Hi, I'm Ed Marzell, President of Kenexis. I've put together this presentation with the objective of providing more information on the new tools and techniques that are available to perform placement of fire and gas detection equipment. These new methods fall under the category of performance-based analysis, which means instead of using rules of thumb and expert judgment to place detectors, we're going to do risk analysis calculations to set performance targets and then verify that those performance targets have been achieved quantitatively. The technical report from ISA 84.00.07, describes this procedure. It provides a safety life cycle for fire and gas system design and also creates a new metric of coverage, which determines the fraction of a desired area that is going to be covered by a given fire detector array or gas detector array. So the new performance-based methods are going to require risk analysis to determine what that coverage target should be, and then quantitative verification that the target has been achieved. Before discussing the topic in more detail, let me tell you a little bit more about myself. As I mentioned, my name is Ed Marzell. I am a professional engineer and I am certified as an ISA 84 expert. I am the president and CEO of Kenexis, and I'm also one of the original founders of the company. I have more than 20 years of experience in the design of instrumented safeguards, including safety instrumented systems, fire and gas detection and suppression systems, alarm systems, relief systems, and so on. I have a strong relationship with ISA. I am on several ISA committees, including the ISA 84 committee, which is the committee that does a lot of the rule drafting and technical report writing surrounding safety instrumented systems. And it is that committee, a working group from that committee, that I had a strong involvement in that developed the technical report for performance-based fire and gas system design. I was also a member of the ISA 91 committee, which has now been folded into ISA 84, which is for instrument classification, and also the ISA 18 committee for alarm system design. So I'm active both at the national level, where formerly I was a director of the ISA safety division, and also at the local level, holding various responsibilities for the Columbus, Ohio section. I'm also an ISA 84 fellow and also an author, a prolific author. I've written dozens of technical papers, and I've also written several books, one of them published through ISA called Safety Integrity Level Selection. I'm also a member of the American Institute of Chemical Engineers, AICHE, and the National Fire Protection Association. And before I started on my professional career, I received a Bachelor of Science degree in chemical engineering from The Ohio State University. Now that I've told you a little bit about myself, let me also tell you just a little bit about Kenexis. Kenexis is a consulting engineering company headquartered in Columbus, Ohio in the US. We're a consultancy that specializes in instrumented safeguard design. Kenexis performs our designs because we have three areas where we are highly specialized, which allows us to develop design basis documents for instrumented safeguards. The first area is hazard and risk analysis. From facilitated studies such as HAZIDs and HAZOPs, all the way through detailed quantitative risk analysis, explosion modeling, dispersion modeling, computational fluid dynamics are areas where Kenexis has a lot of expertise. But we also have expertise in general chemical process engineering. We understand chemical reactions, unit operations, and the equipment that are used in chemical process industries. And then finally, we also have a very strong knowledge of control systems engineering. And it's the combination of these three areas of expertise that uniquely allow Kenexis to analyze a facility, analyze the risks of that facility in order to develop a concrete design basis specification for the instrumentation and control systems that are required to protect that facility. All critical instrumentation that's used for safety purposes, those control systems need some sort of basis of safety. Basis of safety is a key term that I'm going to use throughout this presentation. What a basis of safety does is it provides a mechanism, a set of rules, a set of criteria that allow you to design that safety critical system, that instrumented safeguard. These rules and criteria help you to make decisions about how many detectors you need, where they need to be placed, what type of technology can be used, how often they need to be tested, what type of maintenance needs to be performed. Those are all critical aspects of the design, and the basis of safety is going to allow you to make those decisions in a systematic and repeatable way. For fire and gas systems, there are two general types of basis of safety development methods. The first method is the prescriptive basis of safety. This is going to include things like the NFPA 72 or EN 54 standard. They provide rules and charts and checklists to allow you to make a design. The other methodology, or the other type of basis of safety, is going to be the performance-based method, which relies on risk assessment. In a performance-based method, you establish a target for the level of performance of the system or the level of performance of the entire facility. In the case of safety instrumented systems or fire and gas systems, you would be looking at metrics like individual risk of fatality. And you then do an assessment of the as-is system to determine whether or not the as-is equipment with no safeguarding is tolerable. And if it's not tolerable, what degree of risk reduction is going to be required in order to make the situation tolerable. And that performance target, or that difference between what is tolerable and the actual situation, that required amount of risk reduction, is going to be the driver for all of the decisions about the instrumented safeguard. When specifically talking about fire and gas system design, there are a lot of prescriptive standards that are employed in the process industry to design fire and gas detection and suppression equipment. These are well-established guidelines for the design of mitigation systems. They're going to provide detailed requirements for things like foam systems, fire water pumps, extinguishers, but they do not provide detailed requirements for fire and gas detection equipment in open processing areas. The prescriptive rules are primarily written for either specific pieces of equipment or, in the case of NFPA 72, for occupied facilities. But open air chemical processing areas are typically not covered by these standards, or not covered well by these standards, and the concept of gas detection is missing from these standards completely. But if you look at the prescriptive standards, even though they are prescriptive, they usually allow for the use of performance-based alternatives where appropriate. And of course, an open air chemical processing facility would be an area where it would be appropriate to use these measures instead of trying to apply the occupied building techniques that are detailed in NFPA 72 or EN 54. These standards, as I've mentioned, are generally not going to be specific to chemical processing facilities. Performance-based standards, as I've already intimated, rely on an assessment of risk to develop performance targets, and those performance targets are typically going to be quantitative in nature. Historically, there have been no detailed standards for gas detection or fire detection with respect to placing detectors for open air chemical processes or oil and gas refining facilities. We've typically relied very much on expert judgment and rules of thumb to perform detector placement. With the advent of the ISA TR 84.00.07 technical report, industry and the experts on the ISA 84 working group have provided more detailed guidance for the design of fire and gas systems, and this design is going to be in accordance with the principles of the ISA 84 standard, or internationally the IEC 61511 standard. What the technical report requests or requires you to do is to specify the level of performance that your fire and gas system is required to achieve, and then quantitatively verify that those targets are actually achieved. The technical report develops two new metrics that are used for defining the performance of a fire and gas detection array. The first one is availability. Availability is very similar to the concept of safety integrity level. It is derived from the probability of failure on demand and calculated the same way as you would calculate that probability of failure on demand for SIL verification purposes. But that is only one part of the problem. The other specification, which is as important, or most would argue much more important than the probability of failure on demand of the electronics, is the coverage, the detector coverage, which is a new metric that the technical report defines and requires to be assigned to fire detection arrays and gas detection arrays. And detector coverage, which will be discussed more in detail later, is essentially a measurement of what fraction of either the release scenarios or the geographic area of the plant, what fraction can be detected by a given gas detection array or fire detection array. The technical report was written primarily for the process industries. Many of the drivers of the development of the technical report are the major and super major oil and gas production companies from around the world. Now, it's important to remember that this technical report is not intended as a replacement for the prescriptive design processes out there like NFPA 72 or EN 54. It's intended as a supplement, and specifically it's intended to be a supplement in areas where the existing prescriptive approaches either don't give any guidance at all with regards to the design, or the guidance is insufficient in some way. So after hearing the discussion of performance-based designs or prescriptive designs, one might want to ask, well, which approach is better? Which one should I use? And the answer is really that a combination of the two is going to be required to solve the problem of fire and gas system design. Many elements of fire and gas system design are adequately addressed by the prescriptive standards. So if you're looking at an offshore oil production facility with a control room, living quarters, other occupied facilities, the design of the fire and gas system inside those occupied facilities, such as smoke detectors and living quarters, those attributes are perfectly well covered by existing prescriptive design basis techniques such as NFPA 72. That being said, many of the elements are either not covered by those prescriptive approaches or would be better designed using performance-based methods. So essentially, when we're looking at open process areas, the existing prescriptive techniques don't really apply very well. And in those areas, we're going to apply prescriptive approaches, or I'm sorry, performance-based approaches. In those areas, we're going to apply performance-based approaches. But in areas where we can apply a prescriptive approach, we will continue to do so. What you see here is the fire and gas design lifecycle as it is presented in the ISA 84.00.07 technical report. You'll see that there are 11 stages in this safety lifecycle. And for those of you that are familiar with quantitative risk analysis methods, you'll see that it's very similar to what you would do in a QRA. This is not by accident, this is by design. Myself and the other members of Working Group 7 of ISA 84's panel that developed this technical report had some knowledge, some grounding in how to perform quantitative risk analyses. And when we were tasked with the problem of how do you design a fire and gas system using performance-based methods, we fell back on what we were familiar with and what we knew, which is a full quantitative risk analysis. Now, that being said, full QRA methods can, and in some cases should be used during performance-based FGS design, but most operating companies use more qualitative or semi-quantitative approaches similar to the level of effort of a LOPA, which we will get into as we spend more time discussing this topic. So looking at the life cycle, we're going to begin by identifying the areas of concern. What are the leak sources? Where can leaks occur from? And those leaks can then ultimately result in fires. Then for each leak source, we're going to identify the risk scenarios, whether it's gas dispersion, toxic gas dispersion, flash fires, jet fires, pool fires. All of those different scenarios are going to be a function of the type of material being released. After that, we're going to analyze the consequences, perform explosion models, fire models, and dispersion models to determine the extents of the release when it occurs. After that, we're going to analyze what is the hazard frequency. So what is the likelihood that a release event will occur? And we're going to do this a little bit differently than you would for a pH or a LOPA. That's coming up in subsequent sections here. Based on that information, we'll do an unmitigated risk assessment. So we'll use that information, the frequency and consequences, to determine the risk of the plant without a fire and gas system being installed. If that level of risk is not tolerable, it's determined not to be tolerable, then we are going to identify what are the fire and gas system risk reduction requirements. How much risk reduction is going to be required to get us to a tolerable risk state. After we do that, we're going to do an initial fire and gas system design. And once that initial fire and gas system design has been laid out, usually using some of those rules of thumb that the current prescriptive method employs. But we're not going to stop there. After we do our initial design using expert judgment and rules of thumb, then we're actually going to do some quantitative analysis. We're going to assess the detector coverage. So we're going to actually calculate what fraction of area or scenarios the existing or the proposed gas detection array or fire detection array can actually see, and then we'll calculate the safety availability using similar methods to ISA 84 technical report 84.00.01 that discuss calculation of probability of failure on demand. And using that information, we'll be able to perform a mitigated risk assessment, or what is the risk considering the beneficial effect of the fire and gas detection system. Using the results of the detector coverage assessment and the safety availability analysis, we'll be able to perform a mitigated risk assessment here. Step 10. With the mitigated risk assessment, what we're doing is calculating the overall risk of the facility considering the beneficial effect of the fire and gas system. If that risk is tolerable, then the design that we came up with is adequate. If that design does not achieve tolerable risk, then we're going to need to modify the fire and gas system design in an iterative fashion until it does achieve the tolerable risk level. Now, the workflow that you would use for a fire and gas system design is going to be slightly different than the life cycle that was laid out in the standard. As I mentioned, when we first wrote the first version of the standard, performance-based fire and gas system design really was not done yet. It was not very prevalent. After having had several years of experience since the release of the standard, or more importantly, since the time when the technical report was being written from 2007 to 2010, we've developed a lot more experience with these processes and have developed more streamlined workflows as shown in this slide. Now, I do expect that with the next release of the ISA 84.00.07 technical report, we're going to see some changes to the life cycle in that document that will be be a little bit more similar to the workflow that you're going to go see, or that you're going to see here. Now, if you look at this workflow, the first thing we're going to do is identify the requirement for a fire and gas system. There are several triggers that would cause you to do the analysis to determine whether or not I need a fire and gas system. After that, we're going to develop a fire and gas system philosophy. Now, that doesn't happen for every project. It's usually something that occurs kind of at the corporate level or at the plant level one time before any project work is undertaken. Now, on a project-to-project basis, where we're really going to start is the zone definition. We're going to take the facility and we're going to break it up into physical areas that have similar risks and similar emergency response actions when a gas release or a fire is detected in that area. For each one of those zones, we're going to determine what are the FGS performance targets. And the performance targets, as stated in the ISA 84.00.07 technical report, are coverage and safety availability. Then we are going to verify the coverage and the availability of either the existing design or the proposed design to determine whether or not the targets have been achieved. If they haven't, we will modify as required until the targets are achieved. After that step, the life cycle of the fire and gas system is very similar to any other instrumented safeguard, whether that be safety instrumented systems or any other control system project for that matter. We're going to prepare design specifications, write procedures for how to interact with the system. We're going to build the system, construction, installation, and commissioning. Before starting the system, we're going to do a validation step, pre-startup acceptance testing, where we confirm that what has been installed in the facility matches with what was specified. And then we'll go into operation mode, where hopefully not a whole lot will happen. We'll do maintenance on a periodic basis and testing to confirm that the system is in operation, and if there are any detected faults, we'll have to go ahead and repair those. And of course, there's always the management of change step. If you make any changes to the facility, you're going to need to make sure that they are done in a safe fashion. We'll have a slide coming up a little bit later on where we talk about this management of change issue, because it is more important for fire and gas systems than many other instrumented safeguards, because literally any change that changes the topography of the facility changes the coverage that's achieved by your fire and gas system, whether that's installing a new pump or something as simple as erecting some scaffolds. It's going to change, and possibly in a detrimental way, the coverage that you achieve with your fire and gas system. The first step in the FGS life cycle is identifying the requirements for fire and gas systems. So why would you install a fire and gas system? What would even get you into making the determination that you need to analyze a system to determine whether or not a fire and gas system is required? There are a lot of process areas where inherently you know that fire and gas systems are not going to be required simply by what their nature is. So there are a few things that are going to trigger the requirement to go into the life cycle. The first one would be requirements from previous safety studies. So HAZOP studies might have a recommendation to consider a fire and gas system. A layer of protection analysis study might require that, or might have made the assumption that a fire and gas system was present and that it achieves a certain level of performance. And quantitative risk analyses. In a lot of cases, different areas of the world, a QRA is performed for every facility, as part of its licensing process to operate. And if that QRA has taken credit for the existence of a fire and gas system, then obviously that fire and gas system would need to be supplied, and it would need to achieve the level of performance that is assumed in the QRA. Now, depending on what region a facility is being built in, there may be government regulations or government requirements to install fire and gas systems. So for instance, in the United States, if you have a facility that processes liquefied petroleum gas, LPG, there's an NFPA code that will require the use of gas detection in the area of that equipment. Now, if those notwithstanding, government regulations notwithstanding, there are also a lot of corporate standards and corporate requirements where an operating company might decide that for everywhere that it has a gas production facility, it's going to apply fire and gas systems. So at the corporate level, there are a lot of requirements. And then finally, requirements might be triggered from insurance providers who go and inspect your facility and then make recommendations that they expect to be completed in order for them to insure your facility. As I've mentioned, fire and gas system philosophy development is something that's going to occur once. It's not going to occur for every project, and it is going to occur more at the corporate level, the higher level, than down at the plants or for a specific project. This is important because you want to make sure that your fire and gas system design is going to be consistent from plant to plant to plant, instead of a design changing different alarm colors or alarm horn sounds for different process areas within the same facility is not only counterproductive, it can actually be quite dangerous. So you're going to want to make sure that a lot of this information is going to be standardized. So again, the philosophy development is something that occurs early on in the process, and it's going to be based on the risk tolerance criteria and HSE philosophy of your facility or of your corporation. And when you finish up with your fire and gas system philosophy, you're going to end up with a philosophy document and several procedures that you're going to use to implement fire and gas system projects. A corporate fire and gas system philosophy will have many elements. And these elements are basically going to be broken into two categories. The first category being standardized methods, and the second category being standardized design heuristics or design procedures, rules of thumb. With respect to the standardized methods, the methods are going to relate to what are the processes and procedures that you're going to use to assess FGS requirements. So there will be criteria for how do you identify hazards, which hazards are present that you need to design for. There will be criteria for how you categorize your risks. So the level of risk associated with a high pressure gas compression unit is going to be that's going to be higher than the risk level for atmospheric diesel storage, for instance. So procedures to determine which risks are higher and require more safeguarding. And then there will also be requirements for what type of safety analysis you're going to perform and what are the actual studies that need to be performed and how are those studies going to be executed. With respect to design heuristics, these are going to be criteria that you design your system to. So there will be criteria for how do you do zone definition and how do you do grading. How do you assign performance targets to your fire and gas system equipment? There will be criteria for determining what type of detectors do you use. When do you use UV versus IR versus triple IR versus CCTV technology? There will be criteria for setting what the alarms are. So when do you alarm? Low alarms, high alarms, what are the settings for those alarms? There will be requirements for manual activation. Where do you put your MACs, your manual alarm call points? How many do you need in a certain location? There will be requirements related to detector voting and how that voting is impacted with respect to alarming and also with respect to executive actions being taken as a result of activation of fire and gas detection equipment. And finally, there will also be criteria for set point selection. So there will be different set points typically for low alarms, for high alarms, or high would be more technically correct, even though the industry jargon generally says low and high alarms. And then also even higher alarms or different alarms that indicate that executive actions need to be taken if that is going to be part of your fire and gas system design. All of this information is something that needs to be decided upon and agreed upon ahead of time by all of the stakeholders in the fire and gas system, from operations to instrumentation and control to the safety department. After you've completed your FGS philosophy documentation, you should have a set of several procedures that you're going to be able to use for designing your FGS. Some of the important ones are going to include procedures for hazard identification. So what tasks are you going to do to identify where there are hazards and what types of hazards are present in any particular zone? There will be procedures for zone definition, defining different areas as zones, and also grading, or the risk analysis process that you're going to use to determine what is the criticality level that is going to then result in performance targets for those different zones. Performance target selection, again, detailed procedures on how do I achieve, or how do I determine what is the coverage and safety availability that's going to be required for a certain zone. And then you're also going to need procedures for how do you verify, quantitatively verify, that you've achieved the performance targets that were specified in the previous step in the FGS safety lifecycle. The next step in the FGS design lifecycle is the step of zone definition. When we're going to define zones, we're going to want to start with documentation about the facility. So things like process flow diagrams, piping and instrumentation diagrams, plot plans. Plot and deck plans are critical because this is a geographic exercise, so we need a geographic description of the facility, and also other documentation like cause and effect diagrams if they're already available. We're then going to use a toolkit process and end up at the end of this zone definition step with a list, an FGS zone list. And that list of zones is what we're going to use for each of the subsequent steps in the project to determine what the requirements are for each individual zone. Zone definition is an important part of the FGS safety lifecycle. The zones are going to be kind of equivalent to safety instrumented functions in safety instrumented system design. They're the basic unit upon which risk analysis is performed. There are several different types of zones, and depending on what the zone is, that will also determine what type of analysis is performed and what requirements end up getting placed on those different areas. So for instance, you may have a living quarter would be an occupied type of zone that for that zone you wouldn't need to do fire and gas mapping. You could simply follow NFPA 72 requirements. There might be another type of zone which is a process area zone, and in process area zones you can't really fall back on the prescriptive standards, and you're going to need to use more of the performance-based techniques. And then there are other types of zones that are kind of intermediate, or what we call separation or segregation zones, where you have an interface between an unprotected area and a protected area. So a great example of that would be an air duct or an air inlet that's going to bring air into a room that has unrated electrical equipment such as motor starters. You're going to want to have a certain set of requirements on gas detection equipment that are going to prevent air from being pulled into that room with unrated electrical equipment that contains hydrocarbons. because if those hydrocarbons were to work their way into that room, the unrated electrical equipment could be a source of ignition. So in addition to separating the area into or your overall plant into different areas with similar risk profiles, we also need to consider zoning with the perspective of first responders. So your alarm system, your displays, your alarm panels are going to also be based on zone. And depending on which alarm is coming from which zone, that's going to give a lot of information to first responders with respect to where is the fire or the gas release located, what type of firefighting means are they going to need to use for that equipment, and what other hazards might be present both in that area and in the surrounding areas. All important information when you're defining the zones for your facility. As I've already mentioned, each zone is going to be categorized. It's one of the first steps that occurs after you physically define what the extents of the zone are. What you're seeing here is not currently in the current version of the ISA 84.00.07 technical report, but I would expect in the next version something similar to this will be available. The zone categories that we have defined here are basically, I would consider them Kenexis best practice, but they're not contained in any technical report or standards document yet. So basically for each zone, we're going to give it a category number, a category name that is going to basically end up defining what procedures am I going to use to design that zone. Am I going to use prescriptive? Am I going to use performance-based? What are the different steps and specifications for equipment that are relevant to that type of zone? So typically, the ones that we recommend using are H, which is a hydrocarbon process area. That's going to have general fire, flammable gas hazards, and depending on what type of fluid you're processing, may also contain toxic hazards. So examples would be production areas, gas compression areas. N would be still a fire hazard, but a non-hydrocarbon fire hazard, something like combustible liquids like methanol storage for methanol injection. G is going to be a general occupancy area where we don't expect hydrocarbon fire hazards, but other fire hazards are present. And this would be things like control rooms and accommodation areas. A type E zone is going to be special equipment that needs protection. Okay, and for the type E zone, the best example I would give you would be non-classified electrical equipment. So the motor control center of a facility could be rated a type E zone. A type T zone is kind of a special area. These are going to be enclosures of the drivers of rotating equipment. So gas turbine enclosures, engine enclosures, all have special requirements. A lot of these requirements are going to come from the equipment vendors that provide these types of pieces of equipment. And the last one commonly used is going to be the V-type zone, which is going to be your air intakes, whether that's ventilation air into a building or combustion air into a piece of fired equipment. Those zones also typically are going to be more prescriptively designed than performance-based design, because the attributes of the zone are well known enough to where prescriptive rules usually can be employed very effectively. At the end of the FGS zone definition exercise, the deliverable from this stage of the life cycle will be an FGS zone list. And here's a typical example of a zone list that would be generated by the one of the Kenexis tools that we use for such activities. And the zone list is going to include things like identifiers for the zones, kind of a tag for the zone, a description of what the zone is, and then also categorization information. So for instance, the last zone down at the bottom here is going to be zone 6, the gas plant process area, and we've determined that that's going to be a type H hydrocarbon zone. So this is a deliverable that's going to set you up for the next step, the analysis phase, where we're going to be picking the performance targets. The next step in the FGS safety life cycle is one of the steps that is very new. Historically, we've divided facilities up into zones because that's established different requirements and also allowed for good reporting of locations of hazards, fires, or gas releases that are occurring. But with the advent of performance-based approaches and the ISA 84.00.07 technical report, we have also added performance targets. So this is something that's new, that hasn't been done previously, and as a result, it's an area where there are a lot of questions about how to perform these different tasks, because these tasks are generally outside of the field of expertise of your typical fire and gas system engineer, kind of heading more toward an HSE role or a quantitative risk analyst role. So when you're determining the FGS performance targets, and again, those targets are going to be both coverage and safety availability, we're going to start by using our FGS philosophy and the procedures contained in those philosophy documents that are going to tell us how to perform the fire and gas system performance target selection. We're probably going to use some sort of toolkit, whether that's a software tool or just, again, referring back to tables in a procedure to assist us in this task. And at the end of the task, we'll have an FGS design basis report that's going to add to that zone list that we created in the previous step. And for each one of those zones, we will assign performance targets either to the zone as a whole or more commonly to every major piece of equipment that resides in that zone. In order to obtain the performance targets for a fire and gas system, you're going to need to model the risk. And there are some requirements that your risk modeling process needs to consider. You need to develop a risk model that is sensitive to two things: the two performance metrics of the fire and gas system, that being the detector coverage and also the safety availability or the probability of failure on demand of the electronics of the fire and gas system. Now, the analysis is also going to need to consider all of the attributes of the loss of containment of a flammable or toxic material. So you're going to need to consider what type of equipment am I using in my facility. That's going to tell you something about what the leak rates are. You're going to need to consider, well, what are the range of consequences that can occur if the material is released? How likely is that release? This is another important attribute. And then some other things are going to define the risk, like what is the level of human occupancy in any particular zone? What is the probability that a release will be ignited? And in some cases, you may also want to consider the production value of a process, or what is the financial loss associated with a loss of containment event. With respect to the details of how performance targets are actually selected, the methodologies that are available fall into two different categories. And those categories are the semi-quantitative approach, which is a similar level of effort to a layer of protection analysis. It's a less precise approach, but can usually be done very quickly and efficiently. And as we'll see later on, if done well, the semi-quantitative approaches, which can happen very quickly, will deliver results that are equivalent to the fully quantitative methods with an order of magnitude or more less effort involved in developing the results. Also, the other approach to use is the full quantitative risk analysis approach. As I mentioned earlier, the full QRA methodology was kind of the starting point as we were developing the standard, but we quickly realized that shortcut methods, semi-quantitative methods were possible that were going to allow you to develop your performance targets much more quickly with a reasonable level of accuracy. And the semi-quantitative approaches are almost universally what every operating company that is currently applying performance-based approaches to design their fire and gas systems. The semi-quantitative approach is what these operating companies are using. Right now, full QRA type analysis to set performance targets for fire and gas systems is really only being done in some special cases, highly toxic materials, for instance. And then also the full QRA approach is going to be used for calibration of semi-quantitative approaches. And the topic of calibration is going to come up again in a few slides. It's an important topic. Regardless of the type of methodology used to select the performance targets are going to be the same. Again, there's going to be coverage and there's going to be safety availability, which is an analog of equipment probability of failure. For fire and gas detector coverage, there are two types, which I will define in more detail later in this presentation. Those two types are geographic coverage, which calculates the fraction of a certain area or volume that is covered by a given array of gas or fire detectors. And then there's scenario coverage, which looks at what is the percentage or the fraction of the release scenarios that are detected by that detector array. It's a subtle difference, but it's quite important. When you're looking at semi-quantitative approaches, you're probably going to use geographic coverage because it's quicker and easier to calculate, whereas the full QRA approaches require you to use scenario coverage. Now, on equipment probability of failure, we use safety availability as the term in the 84.00.07 standard. The safety availability, again, is very well correlated to SIL, but the working group that wrote the technical report, myself included, felt that using SIL on a fire and gas system is not really appropriate because there are a lot of qualitative aspects and attributes of a safety integrity level that really don't fit very well with a fire and gas detection and suppression system. Things like fault tolerance, minimum fault tolerance, is not something that you can or even should apply to a fire and gas system. The concept of redundancy in a fire and gas system necessarily needs to be handled differently in a fire and gas system than in a safety instrumented system because of that additional coverage component. So safety availability is what we use, and then we're going to verify that we achieve these targets. So for probability of failure on demand, you might use whatever SIL calculation methods that you currently use, whether that's fault trees or Markov models or simplified equations. And then for coverage, and what you see here is an example of geographic coverage. You're going to need to perform calculations, usually using computer-aided tools, but it is possible to do this type of analysis using manually, using drawings, and I'll explain that a little bit later in the discussion. But this type of analysis is what we're going to use to verify that the coverage has been achieved.
I'm going to explain the fully quantitative approach to FGS performance target selection first. And that's because in order to really appreciate the semi-quantitative method and understand why the semi-quantitative method can deliver similar results to the fully quantitative approach with significantly less effort, you need to really understand first what occurs in the fully quantitative approach and then how shortcuts are taken to represent what occurs in the fully quantitative approach for the semi-quantitative approach. In fully quantitative analysis, again, a full QRA, full quantitative risk analysis used to select fire and gas system performance targets, We first need to characterize the consequences of a release of material from process equipment. We're going to do that through dispersion and consequence modeling. Sometimes we'll use similarity models like FAST from DNV. In other cases, we may want to use computational fluid dynamics to more accurately characterize the releases, especially in situations where the releases occur indoors, where the size and direction of flow of the gas cloud is going to be more dependent on mechanical ventilation than on the characteristics of the plant or the weather conditions. We're going to look at release likelihood through an equipment failure rate database. More on that later. We're going to look at mitigating factors that vary from site to site that are going to impact the magnitude of a consequence given a release has occurred. Things like probability of ignition, degree of congestion and confinement. And after we do all of that modeling, we're going to calculate the overall risk of the zone and compare that against tolerability criteria. The design criteria then are going to be iteratively modified in order to achieve the tolerable risk target. So we'll run the calculations for the first case. If we don't achieve tolerable risk, then we'll need to add detectors, move detectors, and so on until tolerable risk is achieved. This analysis for the full quantitative approach is going to necessarily be based on scenario coverage and safety availability. Geographic coverage is a shortcut approach that is going to be very useful for the semi-quantitative approaches, but when you're doing the full QRA, you need to actually look at individual scenarios. The full QRA approach starts with hazard scenario identification. So what we would need to do is look at a zone, look at all of the release points, and then determine all of the credible scenarios. So for each vessel, piping, flanges, instruments, instrument connections, wellheads, pumps, compressors, exchangers, launchers, receivers, risers, pipelines. The list goes on and on of all the types of equipment that you would need to consider in your zone. So those are the release points. And then for each release point, we're going to need to look at the factors that are going to affect the release size. So we'll consider potential hole sizes in the equipment that the leak is occurring through, the location and orientation of the equipment and the release, the phase of the release, whether it's gas, liquid, or a combination of the two, the degree of toxicity of the material if it's toxic, and the occupancy of the zone. The result of this analysis should be a very detailed list with enough detail, again, to undertake the consequence and likelihood analysis. And then for each one of these releases on the list, you would need to look at all the potential incident outcomes. So for single release, you could end up with a toxic gas exposure, a flash fire, a vapor cloud explosion, a jet fire, a pool fire, and so on. All of the relevant modes need to be modeled. As you can imagine, if you take a look at all of those parameters, for a single zone, there could literally be millions or tens of millions of calculations that need to be performed to accumulate all that data. Now granted, the great bulk of these calculations can be done automatically through consequence analysis software, but nevertheless, the amount of effort that's required to do this type of analysis really can't be understated. After the consequence analysis is completed, the next step is to perform the likelihood analysis. Now, likelihood analysis is going to be performed differently than what we think about for other instrumented safeguard studies such as LOPAs to determine SIS requirements. The LOPAs and the fault trees and the HAZOPs, all those methodologies are predictive. They start with initiating events, then consider other factors, and use that combination of logic to predict the frequency at which they expect a certain subsequent event to occur. For fire and gas system design, we can't do that because inherently we install fire and gas systems to protect against scenarios that we cannot predict ahead of time. Scenarios that we know about, the known unknowns, the well understood potential hazard scenarios. If we know that a scenario can happen, we want to ensure that the risk of that scenario is tolerable using preventive means, not using mitigative fire and gas means. But as a result, we still need to consider all of the unknown unknowns, or the release scenarios that we really couldn't have predicted during the design phase of the plant. And instead of doing an inference technique where we run calculations to predict, we're simply going to look at historical data. We can look at historical offshore release data, such as offshore release statistics from the UK Health and Safety Executive. Parlock 2001 is another source of data that can be used that basically looks at individual equipment items and says, historically, how often does this type of device or this type of equipment item leak? And when it does leak, what is the hole size? So you'll take those frequencies of release and you'll be able to distribute them into different hole sizes. And again, this data, it's critical that this data needs to be sensitive to equipment type. So as you're doing a likelihood analysis, you'll simply list all of the equipment items that are in a particular zone and then use databases to calculate how frequently we expect them to leak, at what hole size we expect them to leak, and then do a summation for the overall zone. Each incident outcome is going to become the final leg of an event tree. So in the risk integration process, we're going to develop an event tree that starts with a release of material and then builds out into all of the incident outcomes that are possible using branches that will change the likelihood of the different outcomes that are going to be possible as a result of a different event. Subsequently, once the event tree is built and quantified, we'll be able to calculate the frequencies at which different levels of harm can occur. So we can calculate the frequency of expected fatalities, the frequency of expected serious injuries, and so on, and then compare those numbers against tolerability of risk targets to ensure that tolerable risk is actually achieved. What you see here is a typical event tree that might be used in a QRA for a chemical process facility. You'll start with the release, and then from the initial release, you'll branch out in different directions depending on the gates. So the first gate in this specific event tree is going to be early ignition, yes or no. And then with respect to the fire and gas system design, the next two rows are critical. And that is the release detected? Meaning, is there a detector in the correct location to detect that the release has occurred, yes or no? And then, and that's shown here. The next item would be the fire and gas system effectiveness, and that's the safety availability, the PFD. Do the electronics actually work given that there's a detector in the proper location, yes or no? And based on the answers to these questions, you'll get sent down a different row for the different outcomes that are possible as the result of a release event. Now, the event tree that you're looking at here is very, very simplified, but it's still more complex than the event tree that's shown in the ISA 84.00.07 technical report. The one that's shown in the technical report really only shows the release detected FGS effectiveness branches are the only things that are in that tree. And it is not meant to demonstrate how the design should occur, but just a symbolic representation of event trees with the two new critical items for fire and gas mapping, which are coverage and safety availability. Now, if you were to do a full QRA approach, your event tree will be much more complex than this. Typically, we see event trees with anywhere from 80 to 250 branches along the side. So this is quite a complex endeavor when you're doing the full QRA approach. Now, for each one of the branches, you'll calculate a frequency. So let's say you start with a release frequency of 2.97 times 10 to the minus 4. You'll go down each of the branches. So let's say we wanted to know what is the frequency at which there is a release with an early ignition, which means we're going to start with a jet fire, but that release is not detected by the gas detection system or the fire detection system because there isn't a fire detector in the correct location. And that would be down this no branch. So in order to calculate the frequency at which that occurs, we will take the release frequency, multiply it by the conditional probability of early ignition, multiply by the conditional probability that the release is not detected by the fire detection equipment to calculate the overall frequency of that branch. Okay. Given that each one of these frequencies will then result in a certain consequence level. So a branch might result in multiple fatalities, single fatalities, injuries, serious injuries, and so on. What we then need to do is to sum up, and again, this is a little bit of a simplified discussion. Typically, you would see rows for fatalities, injuries, serious injuries, and so on. What you would need to do then is to sum all of the frequencies. In this case, we're just going to sum all of them together to determine the overall frequency for a certain type of outcome. And then you can then take that number, so let's say 2.97 times 10 to the minus 4 was the frequency of fatality. You would then take that number and compare it against your tolerable risk target, possibly 1 times 10 to the minus 4, and then you would see that the actual frequency is greater than the tolerable frequency, so something needs to be changed in order to make that level of risk tolerable. And the numbers that we can change in order to make the risk tolerable are the release detected, or the detector coverage, and the FGS safety availability numbers. So you can manipulate those two numbers until the tolerable risk level is achieved. And in that way, you'll be able to establish those two critical performance targets for your fire and gas system. Now that I've demonstrated the fully quantitative approach, I want to demonstrate the semi-quantitative approach, given that you have more of a background now in what occurs in the full QRA, so you could see how we shortcut that to significantly reduce the amount of effort required to select performance targets, yet do it in such a way that the tolerable risk level can still be, you can still be comfortable that the tolerable risk level is achieved. So for the semi-quantitative approach, it's going to be a team-based assessment where you're going to use calibrated risk tables, calibrated being the key word there. What you're going to do is you're going to look at different attributes that define the risk of a facility, such as equipment type, temperatures, pressures, phases of material release, ignition conditions at the facility, confinement conditions, and for each one of those handful, maybe 5 to 7 parameters, instead of strictly defining what it is numerically, you're going to put it into a range. So instead of saying that the temperature is 250 degrees Fahrenheit, you're going to say that the temperature of the material is between 500 and 1,000 degrees Fahrenheit. Put it into different bands. And each one of those bands is going to have a score associated with it. So you'll look at the different risk factors, pick a category for that risk factor, then combine them all together to get a numeric score. And that numeric score is going to result in a zone grade. Now again, looking at these grades that you're seeing here, these are Kenexis best practice, if you will. And these are actually calibrated. These have been calibrated through multiple customer studies for oil and gas production facilities, both offshore and onshore. Are they appropriate for your specific facility? They may be, they may not be. They're kind of a generic industry average number. I would highly recommend that each organization calibrates for its own operations. I'll talk about calibration in just a second. Now again, these targets are things that need to be defined by a company. You won't see this table in the ISA 84.00.07 technical report, or at least the current version. We expect the next version of the technical report to include a sample semi-quantitative approach with tables and with grading and coverage targets. But it's not there at the moment. So what you're seeing here is some best practice based on a lot of projects that Kenexis has done. So all of those risk factors are going to combine together to give you a score that translates into a grade. So if you look at grade A, that would be kind of a high risk. So in the offshore oil and gas production industry, you might want to think about something like a high pressure gas compression module. Frequent leaks, and when leaks occur, the consequences can be very severe. So there we would assign a coverage, a geographic coverage of 90% and a safety availability of 95%. Kind of a high SIL 1 equivalent. For a grade B, that's a medium risk. Think about something like a well bay or a separator zone. There we would assign an 80% coverage for geographic coverage and 90% safety availability. Grade C would be something that has a lower risk, so you're going to want to think about something like a diesel storage zone or a methanol storage, kind of atmospheric, flammable, on the edge of flammable or combustible materials. There we're looking at a 60% coverage and a 90% safety availability. Now the process that you would use to both create the tables of risk factors and the grades associated is something that your company is going to need to develop itself, but we do have some good information to get you started. So if you look at the Kenexis Fire and Gas Systems Engineering Handbook, which is available from Kenexis on request for a printed copy, and we can also provide you an electronic copy. You can just download that from our website. You'll see that we have different, or a sample categorization process contained inside the document, including flow charts and the different tables. So we have a starting point for you to use in this book, but again, I would highly recommend that each organization does its own calibration to make sure that these targets are going to allow you to achieve tolerable risk. Now, I'm sure a lot of you that are familiar with quantitative risk analysis are looking at the simplified approach saying, wow, you're talking about orders of magnitude less work. You could probably run through those semi-quantitative worksheets with a single engineer who has data. You probably don't even need a team, and you're going to do it in minutes, whereas the full QRA approach could take hours or days to develop the same amount of work. And it's great that you have all these tables with the scores, but how do I know that the numbers in the table, the tables that developed the targets, the targets themselves associated with the different grades, how do I connect the dots between what's in those tables and what is actually truly tolerable risk? Because just looking at the semi-quantitative approach in isolation, you would have to say that there's no correlation between that approach and quantitative risk. It's all kind of subjective. You just picked some numbers. Well, the truth is we didn't just pick numbers, and that brings up the very important topic of calibration. And again, that's why I discussed the fully quantitative approach first instead of just describing the semi-quantitative approach. For the fully quantitative approach, you actually do achieve tolerable risks. In the semi-quantitative, you're picking numbers that are giving you scores that are going to result in targets, and you simply have to have faith in the semi-quantitative approach that it's actually going to achieve tolerable risk. Well, in reality, you don't have to have faith as long as you have done a proper calibration. So what a calibration does, giving you the overview, is the first step is to start with a semi-quantitative approach that has tables for risk parameters and tables for zone gradings, and then perform an analysis using that semi-quantitative approach. But you don't stop there. You also take those zones. So you would pick some typical zones that are typical of your production environment. You might do, if you're an oil and gas producer, you might do some wellhead zones, some separator zones, some gas compression modules, maybe one of each, and run it through the semi-quantitative approach, but then also run those same exact zones through the fully quantitative approach. So you're going to analyze those zones two different ways, once fully quantitative, once semi-quantitative. For an uncalibrated procedure, they're probably not going to result in the same answer in both cases. If they don't, and usually as a starting point they don't, then you're going to need to go back to your semi-quantitative approach and make adjustments. You'll need to adjust the ranges inside the risk factor tables, and you'll need to vary the performance targets in the different grades. And you're going to need to keep doing that until consistently the semi-quantitative and the fully quantitative provide the same results. At that point in time, you can consider your semi-quantitative approach to be calibrated to achieve your tolerable risk profile. And the reason it's important for each company to do this individually is because operating parameters vary from facility to facility. Some facilities are built with more risk than others inherently. And also, different operators are willing to accept different levels of risk in their operations. So each individual operating company should really have their own calibrated semi-quantitative procedures. What's in the Kenexis FGS Engineering Handbook is a good starting point. It has been calibrated to some generic industrial norms, but we highly recommend that each company do their own calibration. Another important attribute of the semi-quantitative approach is the extents of graded area concept. One of the weaknesses of the semi-quantitative approach is that, or not only the semi-quantitative approach, but also just geographic coverage in general, is that you're not really considering where the leaks are coming from when you're deciding where to assign your coverage, your gas coverage or your fire coverage. You're basically, covering everything. You'll do a whole zone, you'll assign a grade to a zone, and then that entire zone is going to be covered equally, when in a lot of cases that doesn't make sense. So in order to make up for that shortcoming, we've developed the concept of graded areas. So if you look at this drawing on the left-hand side here, you'll see that this is a typical production facility that we use in our training classes. It has a couple of separators, a compressor, and a pump. Very simple facility. But you'll see that, well, in this area over here, there is no process equipment. Now, if I took this whole rectangle and called it a single zone, I would need to supply fire and gas coverage over here in this area where there is no equipment. There's nowhere for a release to occur. Why do I need to cover that? Also, you'll want to say that, well, I definitely want to cover the compressor with more rigor than I want to cover a low pressure separator. the risk is a lot lower. Why am I covering high risk areas and low risk areas with the same degree of coverage? And in order to make up for all of these attributes, what we can do is we can do extensive graded area. Now, how extensive graded area works is it's similar to electrical area classification. So in a project, you would list out not all the zones, but per zone, each individual equipment item, or major equipment. In this case, we have 4, 2 separator vessels, a compressor, and a pump. And for each one of those equipment items, we would do that semi-quantitative analysis process to assign a grade not to the zone as a whole, but to that individual piece of equipment. And then for that piece of equipment, we would set off a certain distance away from that piece of equipment to be required to be covered to that grade. So if you look at this compressor, the area that's shown in red around the compressor would be grade A because that's what was selected. And then also an area around that would be a lower grade. So this is, if you think about it, this is very close to electrical area classification, where you identify all of your leak sources and then you'll have a certain standoff area away from that leak source where you would want in the case of electrical area classification, it would define the ratings of the electrical equipment. In this case, it would define the coverage that a fire detector array or a gas detector array would need to provide for that piece of equipment. So this allows us to really focus on the areas where the risk exists and cover lesser risk areas with lower rigor, and potentially even not cover areas that don't have any risks associated with them. So you'll see the grading map on the left-hand side. On the right-hand side, you'll actually see an effigy fire detection map for that same facility, with the blue lines representing the edges of the different grades, and the map itself. Red means that there's no coverage, yellow means that one detector covers that area, green means that 2 or more detectors covers that area. And in this way, you can calculate the numerical coverage for each of the different grades inside the zone to make sure that the coverage is acceptable. So you'll see here that this giant area of red is not covered at all, but also it's not graded. So that's okay. It's not graded because there's no equipment there that's going to form a leak. So the extensive graded area concept is what allows the semi-quantitative approaches and the geographic coverage to more accurately place detectors in areas where the leaks are actually going to be occurring, as opposed to a fully quantitative approach where you're looking at scenarios, and there you're actually looking at the extent of a release. But again, that scenario coverage and fully quantitative performance target selection is a lot more time consuming and typically not done by a lot of operating companies at this point in time. After performance targets have been selected, the next step is to verify that the coverage target has been achieved by the actual fire detector array or gas detector array. In terms of verifying detector coverage, we're going to start with the philosophy and procedures that have been developed to allow you to achieve coverage, and then we'll perform that task using usually some sort of computer modeling tool that will run the coverage calculations. But again, that can be done manually. The manual methods have, shall we say, a significant degree of inaccuracy associated with them. But then again, even the manual methods are going to be a dramatic improvement over simple rules of thumb or expert judgment.
At the end of the detector coverage step, you're going to have a fire and gas detector mapping report that's going to include for each zone a map that will visually show you what coverage is achieved, along with numerical criteria that define numerically what the coverage is that has been achieved, and a comparison of that coverage against the targets. Verification of detector coverage is a new attribute in performance-based fire and gas system design. Quantitative verification that coverage targets have been achieved is a new and integral part of the ISA 84.00.07 technical report and the Lifecycle for performance-based fire and gas system design. Originally, a lot of practitioners of fire and gas systems, who are mainly instrumentation and control engineers, wanted to apply the design attributes of the IEC 61511 standard and the concept of SIL to fire and gas systems. But SIL by itself does not adequately describe the amount of risk reduction that a fire and gas system can provide, because it only looked at one of the two key modes in which a fire and gas system can fail. The first mode is, again, what is addressed by the SIL, or the probability of failure on demand of the electronics. But the other mode of failure that is not common to other SIS equipment is the failure to have a detector in the correct location. So inadequate coverage and inadequate safety availability both contribute to the amount of risk reduction that a fire and gas system can provide, not just the SIL. So in order to ensure that the fire and gas system provides an appropriate amount of risk reduction, we're going to want to ensure that coverage is going to be adequate throughout the entire life cycle of a facility. Verifying that detector coverage is appropriate is going to include looking at the locations and orientations of the fire and gas detection equipment to make sure that their coverage footprint is suitable. And it's also going to involve looking at the obstructions or the locations of other equipment, such as pipework or vessels that might impede the views of fire and gas detection equipment to be able to perform their functions. The ISA 84.00.07 technical report on performance-based fire and gas mapping defines two different types of fire and gas mapping, those being geographic coverage and scenario coverage. For geographic coverage, the definition is the fraction of the geometric area at a given elevation of analysis of a defined monitored process area that, if a release were to occur in a given geographic location, would be detected by the release detection equipment considering the defined voting arrangement. Simplifying that, if you consider the floor space of an area to be the analysis of elevation, what you'd want to know is what fraction of that floor space can be seen by the fire detector array or the gas detector array. For geographic coverage, it's much, much easier to calculate because all you need to know are the performance attributes of the detectors and their locations and orientations, and also the locations of the obstructions. The actual releases are not relevant to the geographic coverage process because you're only detecting what can be seen as opposed to what can occur. In order to know what can occur, now we need to look at scenario coverage. Scenario coverage is the fraction of the release scenarios that would occur as a result of the loss of containment from items of equipment of a defined and monitored process area that can be detected by release detection equipment considering the frequency and magnitude of the release scenarios and the defined voting arrangement. So for scenario coverage, we're going to look at those hundreds of thousands or millions of gas clouds that we calculate during the full QRA type of approach. For each one of those gas clouds, we're going to compare it against the fire detection array, gas detection array, and determine whether or not that scenario can be seen. If it can be seen, we take its frequency and consider it to be detected. If it cannot be seen, we take its frequency and consider it to be undetected. We then go through every one of all of those scenarios and do a summation to calculate what is the overall fraction of the release frequency that can be detected. FGS detector mapping can either be performed manually, or more commonly it's done using computer software. Either way, the process is roughly similar. The starting point to the process is to look at the performance of a specific detector. The performance attributes of different detectors, especially if you're looking at something like an optical fire detector, are going to be based on FM approval testing data. There is an FM 3260 standardized test that will create a cone of vision for a fire detector, such as what you see on the right-hand side here. So for this particular equipment vendor, you'll see that there are 3 separate cones of vision for maximum, medium, and minimum sensitivity. Those cones of vision from the detector need to be accurately reproduced in the fire and gas mapping software. And you'll see here an effigy screenshot where we looked at the performance attributes of that specific make and model of detector at the 3 different sensitivity settings, and we were able to faithfully reproduce those results in all 3 of the different cases. Now, the cone of vision that you're seeing here that is provided by the equipment vendor based on that FM 3260 test only happens in a very specific case, and that specific case is typically not how the detector is installed. So this cone of vision that you get from the equipment vendor represents a situation that you would never actually install your detector on. What you're seeing here, and the only situation under which this cone of vision is actually valid, is if the detector is mounted at exactly the same elevation that is the elevation of interest that you're running your calculations for. Furthermore, the detector and the plane of interest need to be parallel. So on the same plane, and the cone of vision needs to be parallel to the plane of interest. Only in that situation are you going to draw that map related to that cone of vision. In reality, your elevation of interest is typically going to be around half a meter, 18 inches off of the ground, which is relatively low. And typically your detectors, when they're installed, are going to be raised up higher in the room or in the zone and then pointed down. When you do that, the cone of vision changes. So to get an accurate coverage map, especially for an optical fire detector, you're going to need to calculate this fully in three dimensions. You're going to need to consider the fact that your detector is elevated and pointed down. Now, since the shape that you're drawing is roughly a cone, what is going to be projected on your elevation of interest is essentially going to be an ellipse. So the way that many of the fire and gas mapping software tools is essentially performing analytical geometry calculations, where we're going to be calculating areas of ellipses essentially. Now, the last component for the fire and gas mapping is to consider the impacts of obstructions. So you're going to have a lot of obstructions in your facility: vessels, pumps, compressors, piping, so on. You need to take each one of those obstructions, break it down into its primitives: spheres, cuboids, cylinders, and so on. And then you're going to need to include that item in the model. So if you look here at this particular figure, you'll see a spherical obstruction in the path of an optical fire detector, and you'll see that that obstruction is essentially going to cast a shadow on the elevation of interest. And that shadow needs to be removed from the footprint for purposes of calculation of the coverage achieved. So this three-step process is essentially what needs to occur in order to perform the detector mapping assessment. The results of an FGS mapping assessment are going to look similar to what you see on the screen here. On the left-hand side of the screen, you're going to see results in a geographic coverage mode. On the right-hand side of the screen, you're going to see results in a scenario coverage mode. For geographic coverage, a detector map is going to tell you where there is no coverage. In this case, that would be anything that's red means none of the fire detectors can see that location. Anything that's yellow means only one of the detectors in that zone can see that location. And anything that's shown in green means that 2 or more detectors can see that location. And again, this is geographic coverage, where we're only concerned with what can the detector see, and we're not so concerned with, well, where are the releases or the fires actually occurring. The top is for fire detectors, and based on the years of experience looking at these maps, I can tell that this map is drawn by two detectors. One detector is located here and it's pointing in that direction. The other detector is down toward the bottom and pointed up. So that's fire detector coverage. Gas detector coverage can be done similarly. Again, red meaning no detectors can see that location, yellow meaning 1, green meaning 2 or more detectors can see that location. Now for detector gas geographic coverage, we're interested in a certain diameter sphere of gas cloud. And the determination of the sphere size that is of interest is a rather complex topic that's covered in the ISA EC56 training class that was developed by Kenexis. But basically, I'll start with the most simplified version would be that we're going to try to detect a gas cloud that is of a size that is significant enough to cause damage to a facility. Depending on the attributes of the facility, that's either going to be 5 meters in diameter or 10 meters in diameter. So what we do in the mapping is we'll essentially look at a point on the map and say, if we're down here in the red, we'll basically look at that point in space and say that, well, I want to detect a gas cloud that has a 5-meter diameter. If the center point of that gas cloud was at this location, would there be a detector in its path that would detect that that gas cloud exists? And for everywhere that you see in red, the answer is no. When you see in yellow, that means that at least one detector will see it. Green means 2 or more. And for this specific fire and gas map, you'll see that there are 2 open path detectors that are kind of giving you this oblong shape, and then there is 1 point detector which is roughly going to give you a circular shape for the coverage area. Now both of these are for geographic coverage. On the right hand side you're going to see a scenario coverage map. For scenario coverage we are interested in not necessarily what areas are covered, but what release scenarios are covered. So in order to do that, we're going to calculate the physical dimensions of the releases that can occur in the zone. And what you're looking at here is just a simple metering station. A gas pipeline comes up out of the ground, goes through a meter, and then back down into the ground. That's the scope of the process equipment that's in this zone. So what we would do is we would take a release, a gas cloud that would be released from a hole in this equipment or piping. And then we need to take the shape of that gas cloud and we need to distribute it geographically. So in the FGS software, we're going to take that release and we're going to spin it around in 3 dimensions in 720 different directions. Also, we're going to consider wind direction. And the way that the FGS software considers wind direction is we're going to weight the direction where the prevailing wind will blow gas clouds more heavily and proportionately as opposed to the directions where the wind is not expected to be occurring. Taking all those factors and combining together, you will generate a figure that looks like this. And with this figure, the different colors represent the frequency at which a gas cloud will exist in that location. And just looking at the colors, anything that's in yellow means that we expect the gas cloud to exist in that location at a frequency of roughly 1 × 10⁻³ per year. As opposed to the dark blue, where we expect the gas cloud to exist in that location at a frequency of only 1 × 10⁻⁵ per year. Every color change here representing a half order of magnitude change in the frequency of occurrence of a gas cloud. The top figure is an unmitigated risk, whereas the bottom figure is a mitigated risk. You'll see that in the bottom figure we have 2 open path detectors that are on either side of the metering skid and parallel to it. And what you see in the figure is a residual risk. So the top is the unmitigated geographic risk. The bottom is the residual geographic risk, or what is the frequency of a gas cloud existing at any particular location that is not detected by the gas detection array. And here you'll see that those numbers are very much smaller. There is no yellow and very little green area in this figure, indicating that the release frequency is closer to 10⁻⁴ and dropping down all the way to negligible or less than 1 × 10⁻⁷, where releases existed previously. In addition to this map is a great tool for visualizing where leaks are going to occur with and without the gas detection equipment. But in addition to this, there will be a calculation of what is the fraction of the release frequency that is detected by the gas detection array. And that frequency number is what you would use, or that percentage of frequency number is what you would use to put into your event tree in a full QRA approach, or you can even use that percentage of frequency number in a semi-quantitative approach also, because a lot more operating companies are seeing a lot of value in the scenario coverage to where they would want to do this preferentially, even though it is a lot more effort, because the data and the information that's provided by the scenario coverage approach is much richer than the information that's provided by the geographic coverage approach. Fire and gas mapping studies can be done manually, but manual methods are going to be subject to the errors that we've already discussed. If you wanted to do a fire and gas mapping study manually, let's start with a fire detector study. You'd begin with a plot plan of the facility, such as the one seen here, which is the plant from the Kenexis training class. And after you get the plot plan of the facility itself, you will need to get a plot, essentially, a cone of vision drawing of the detector of interest. Now, you're going to need to make sure that the scale of the plot plan and the scale of the printout of the cone of vision of the detector is the same. Then, after you get your printout, simply use your kindergarten skills and cut the cone of vision out and use it as a template. So we will start with our template of our cone of vision there, and then we will pick the location where we want to see a detector. So let's say we wanted a detector in this location. We would simply take that cone of vision and trace it onto the plot plan, like so. And again, we would then do that for as many detectors as we would want to put on the facility. So in this case, there's only the one detector, and it's pointed in this direction. So that's the view of the detection. And again, the error is going to be because the cone of vision has not been tilted into 3 dimensions. But again, it's better than not doing any mapping at all. Now, in addition, you will need to do some analysis of the obstructions. And in order to analyze the obstructions, you'll want to take a straight edge and go from the point of the detector through the edge of any obstructions and create a line segment. So from here back, this area gets dropped out of the coverage. So only this portion of the area is what we know is going to be covered. Now, if you wanted to be a little bit more sophisticated, you can do some math and calculate a distance, use typical, just traditional trigonometry to calculate the distance at which the shadow that is cast by this piece of equipment would cross the plane of interest, because there's a point in time where we would expect that because the detector is located in an elevated position, that it will be able to eventually see behind an obstruction just based on the angle. So we would use some math to calculate what that is. Let's say that the distance is here. Again, it would be more of a straight line, and then we could possibly say that, okay, this area is also going to be covered, trying to do a little tiny bit of simulation of 3 dimensions. Now, while this is done manually, there are some of the less sophisticated fire and gas mapping software essentially do exactly the same thing as I just discussed. Manual methods, again, they're going to provide some degree of coverage calculation, but at the end of the day, you're still going to need to kind of qualitatively assess, well, the shaded area here, well, what fraction of the entire covered area is that I've calculated? So as you can see, it's a little bit less than accurate, kind of time consuming, which is why most people that perform fire and gas mapping go ahead and use fire and gas mapping software for this task. Fire and gas mapping exercises determination of the actual coverage that is achieved by different gas detection rays is much more accurately done using fire and gas mapping software, such as the Kenexis FGS software that's part of the Kenexis safety instrumented Kenexis instrumented safeguard suite of software applications. So what you would want to do is to determine the level of detection that's available. What I've got here is just a sample well bay, 20, I believe, 20 wells, 20 slots in the well bay, with each wellhead being a leak source, or a point where a leak can occur. If I could show you the layout. So this is the layout of the area. And also you can see that if I can zoom in a little bit, you can see where all the gas detectors have been located, and then you can also see in this location here an optical fire detector that covers the area in question. Now that's the gas detection layout, and all that equipment was placed just using a simple tabular approach. So here we have a couple of fire detectors, and here are the gas detectors that are included in the study that result in this particular layout. And then we would simply run calculations to determine the different coverages. So you can see here the fire geographic coverage, again with the same key with
greens meaning 2 or more detectors can see the area, yellow meaning only 1 detector, and red meaning that none of the detectors can see the area. And you can actually also see the different targets. So as the zone as a total has 48% that is covered by 2 or more, 43% that is covered by at least 1. Totaling both of those together is going to give you a coverage greater than 90% for fire detection. And we can even look at different zones individually. So if I wanted only to see the zones that are graded B, we're able to show you that coverage also. Gas detector coverage is going to be shown in a similar fashion, both with the tabular results and also the geographic map that you can look at in order to determine whether or not your coverage targets have been met. And then if they are not met, you have a little bit more information to determine, well, where are my weak points? Where do I need to put more detectors? With regards to scenario coverage, we would want to look at, let's just say, gas geographic risk. Again, here for a well bay, the risk is relatively high, with right there in the middle of the well bay. And again, using my experience to look at this, the wind conditions are pretty evenly distributed. You're not seeing wind, a lot more wind from one direction than another. So fairly well distributed wind. So right in the middle of the module is where we expect to see the highest frequency of gas releases. And again, this is unmitigated. It does not consider the beneficial effect of the detection equipment. If I then go into the residual risk figure, you'll see the calculation has been performed where every release that is detected by one of these detectors is thrown out of the analysis, and now all you see is on the outside ring essentially are releases that are not detected by the fixed gas detection system. And in this case, these are the releases that are on the outside edge. So if this wellhead were to have a release in this direction, that would not be detected by any of these detectors. And in this particular case, those would have gone off the platform and wouldn't form that great of a risk. But in any case, that's how these things are determined. So you'll see that in addition to the colorized map that you get that shows you, gives you a physical feeling for where the releases that are undetected are occurring, you also have a scenario coverage factor here. In this case, 92.7% of the release frequency that occurs is detected by this gas detection array. Okay, so this is an example of the type of software that you would use to perform these coverage calculations. And specifically, we're looking at FGS, which we believe to be the most sophisticated modeling package available for doing this type of work. After verifying that the coverage targets have been achieved, the next step in the safety life cycle is verifying that the safety availability has been achieved. The safety availability calculation is nearly identical to the probability of failure on demand calculations that would be required to be performed for any safety instrumented function that is designed in accordance with the IEC 61511 ISA 84 standard. So you'll start with a list of functions that you have, and you'll perform your FGS availability using either some sort of software tool, spreadsheets, even hand calculations can be done to perform these calculations, and the result of the task would be a reporting for every FGS function of what safety availability it achieved and a comparison of that against the performance target. There are a number of factors that are going to impact the safety availability that can be achieved by an FGS function. Starting with the type of component. Each component is going to have its own failure characteristics in terms of overall failure rate, safe versus dangerous distribution, and diagnostic coverage of different types of failures. Then you're going to need to consider the degree of fault tolerance. So what type of voting arrangement are you using, and what type of fault tolerance is built into the equipment itself. What type of redundancy do the equipment items contain internally? The next thing would be the functional test interval. The more frequently a device is tested, the shorter the duration that that device remains in the dangerous or failed state, which decreases its overall probability of failure on demand. We're also going to want to consider common cause failures in our analysis, or a single failure that can cause multiple redundant components to fail at the same time for the same reason. And also, I've alluded to this already, you're going to want to consider diagnostic coverage in your calculations. A lot of equipment, a lot of FGS instrumentation specifically, is built with a lot of internal diagnostics that can diagnose failures while the instrument is in operation without a manual functional test being required to perform that assessment. So when all of these factors are considered using anything from a hand calculation all the way through the most sophisticated software, you'll end up with a calculation of probability of failure on demand, which can easily be converted over to safety availability, which is the target that is prescribed in the ISA 84.00.07 technical report, where SIL verification calculations or safety availability calculations are required.
The balance of the FGS safety life cycle is very similar to any other safety instrumented system design project or any other control system design project for that matter. It begins with detailed design and specifications. These are going to include things like loop sheets, wiring diagrams, cable schedules, and even PLC programming. Nailing down the details of what equipment is going to be installed, how it is going to be installed, and making sure that it is configured and programmed. The next step would be the development of procedures for how you interact with the system that is going to be built. So that's going to include operation procedures. So for a fire and gas system, operation procedures would be things like, how do we start it up? How do we acknowledge alarms? How do we reset trip actions that have been occurred? How do we put something into bypass so that we can do maintenance on it? We're also going to need procedures for how do you respond to a detected or a revealed, a diagnosed failure of the fire and gas system. And then we'll also need to write procedures for maintenance activities and the periodic proof testing that is going to need to occur on the system and its sensors. The next step would be actually building the system, construction, installation, and commissioning. In this phase, you're going to need to actually select, requisition, and purchase the actual devices that you're going to use. You'll need to take all of these devices and install them at the site and connect the wiring together. Now, this is critical for fire and gas systems because fire detectors and gas detectors, the performance levels, that coverage target that we need to achieve is very, very dependent on a specific location and orientation. So that information needs to be carefully considered during this phase of the project. You're also then going to need to load the software into any programmable devices and connect the wiring. After that, prior to starting up the plant, you're going to want to do some sort of validation or a pre-startup acceptance test. During this phase, you're going to verify that all of the installed equipment and software conforms to the FGS safety requirements specification. You're also going to want to review all the software and hardware to make sure that it has been designed properly. You're going to want to review all the relevant equipment in the field. So one of the key things that we're looking at during a validation or a PSAT is making sure that the coverage map that we built during the design phase is going to be true for the installed equipment, which is also going to be a function not only of the FGS equipment, but also the physical orientation of pumps and compressors and piping and vessels that the plant is constructed from. And during this phase, if there are any deviations that are noted between the specification and what was installed in the field, those need to be punched out. You need to generate a deviation record and then resolve all the deviations prior to starting up the plant. The next step would be the operation and maintenance phase. And during the operation and maintenance phase, the objective is to do nothing. Our greatest desire is to have spent the required money to develop a very robust fire and gas detection and suppression system that we will never use because there is never a release. So hopefully we would want to do nothing. But if the need calls, we want to make sure that the equipment is capable of performing its actions. So in order to do that during the design phase, we will be, or I'm sorry, during the operation and maintenance phase, we will be responding to overt faults and then also doing some periodic function testing. And then finally, the last step is management of change. And now management of change is an interesting topic for fire and gas systems because it is so pervasive. As you can imagine based on our discussions, the coverage that's achieved by a fire and gas detector array is very, very dependent on the physical layout of the plant. So anything that changes the physical layout of the plant is going to change the coverage. That could be something as big as adding a new compressor or a new pump, or something as small and seemingly insignificant as erecting some scaffolding. All of these changes are going to alter the coverage that's achieved. And what coverage is actually achieved is something that you're going to need to know during that management of change process to determine if the change can be made safely while still achieving tolerable risk. And with that, we come to the end of our presentation. I hope that you found this presentation to be educational and useful. If you have any further questions, you can always feel free to contact me directly, Ed Marzell, at Kenexis. My email address is shown here. You can feel free to email me. Or if you want to just send a general request into our info account, those requests will also be forwarded to the proper person and replied to. Thank you again, and be safe.